So depending on the type of the problem, so problem types. So of course the most general case is nonlinear programming. Or nonlinear optimization. In which the constraints could be nonlinear and the objective could also be nonlinear, and this is the most general case. And the algorithms for nonlinear programming usually work for other cases also, but they might be slow or they might not always converge, as we shall see later on. So if you have a specific problem type and you are able to identify the problem type, then sometimes it is better to look at algorithms which work only for that type. So such problems are quite useful in practice. Main ones are the quadratic programming. In quadratic programming, objective function is a quadratic function, and constraints, either there are no constraints or the constraints have only linear functions. So even though the name is quadratic programming, the constraints still must be linear for these types of problems. And you can also call it quadratic optimization. Linear programming is even simpler. So objective and constraints both linear functions only. So that means I can't take sine x or log x or x square and so on and so forth, or x1 times x2, etc. Related to linear programming is this class of problems called linear constraint programming. And in this case, the constraints are linear, but the objective function could possibly be nonlinear. So we have these different classes of problems because we will look at some specialized methods to solve these problems, and these problems are pretty big classes in themselves, in the sense that many practical problems can be modeled as quadratic programs or linear programs or linear constraint programs. So it is okay to develop customized algorithms for these specific types of problems, and when you see these specific types of problems, then you can directly deploy those algorithms and get a solution. So for example, a general nonlinear programming algorithm may only converge to a local solution in the limit. Eventually it will converge after several iterations, and sometimes it might converge only in the limit. However, if I have a linear programming problem, I can devise algorithms which will have finite termination, in the sense that after a fixed number of iterations we are guaranteed that we will stop. So before we end discussing this chapter, there is one more terminology, which is the term for active and inactive constraints. So given a point x, a constraint, let's say C1x is active if I'm at the boundary of this constraint. Okay, so what that means is that C1 x bar has to be 0. Okay, otherwise it is inactive. Otherwise C1 x less than equal to 0 is inactive at x bar. So so whenever C1 x bar is less than 0, okay, we say that the constraint is inactive. And this terminology will come useful in a certain class of methods called active set methods, where we try to find out or we try to guess which constraints will be active at the optimal point, and then solve a system of equations or nonlinear equations for only those constraints and try to get the solution. Okay, this notion of active constraints is also very important when we talk about duality and sensitivity of the problem to constraints. Okay, so geometrically, suppose I have some nonlinear constraint. Suppose I say x1 square plus x2 square less than equal to 1, and if I look at the feasible region, it's the region inside a circle. X1 x2 are on my axis. So this constraint is active at but inactive at say half comma half. Okay, so we say that this constraint is inactive at half but active at -1 0. So if before we go on to linear programming, I would like to discuss the geometry of the gradient. So recall that if I plot the contours of a function f, so let's say this is saying f equal to 1, and if I look at any point and draw a tangent at this point, the gradient is the normal to this tangent in the direction where the function is increasing. So that means the inside curve is f equal to 2. Okay, and it is decreasing in the direction of the negative of the gradient. So that relation helps us to identify the feasible region for a nonlinear constraint. So for example, suppose I have a constraint of this form, x2 is less than equal to x1 square. So so to plot the feasible region, I can draw this curve, and at any point we can draw the tangent, and this curve in the standard form would be x1 square minus x2 greater than equal to 0. So I need to bring it in the greater than equal to form, and then I take the gradient, and it is pointing in this direction. So that means everything below this curve is the feasible region. Okay, so the feasible region is denoted by the green curve here. Okay, so hope that is clear, and you will be able to practice drawing things and understanding the geometry of feasible sets yourself. So so we will end this lecture with a small discussion on linear programming. So a linear program is an optimization problem in which the objective function is linear. So let me write an example of a linear program. And minus x1 plus x2 greater than equal to minus 3. So if you notice that the objective function is linear in x1 and x2, and all my constraints, if I look at the non-constant part of each constraint, it's a linear function. Okay, so all functions in my optimization problem, if they are linear in variables, then we call it a linear optimization problem. It can be written in two equivalent forms. The most general form is when you have bounds on all constraints. So let me write it, and then we can understand it a little bit more. So c1 x1 plus c2 x2 subject to, so I'm going to write my first constraint in terms of some coefficients multiplied to each variable. So I have some linear function, and I'm saying that it must lie between d1 and h1. Similarly, constraint number 2 is saying that some linear function should lie between two given constants, and so on and so forth. And let's assume there are m such constraints. Okay, so m n are finite. So here C, D and H are vectors. C is of size n cross 1. D and H are size m cross 1. So that means 1 column and m rows. All these coefficients can be thought of as a matrix which is of size m cross n. Okay, so C, D, H and A are given to us. Okay, sometimes we also have, in addition to these constraints, bounds on variables. So I may have x1 less than equal to u1 less than equal to l1, x2 less than equal to u2 greater than equal to so this is the most general form where you have some bounds on variables on both sides and some bounds on linear functions on both sides. It is possible that some of these bounds are infinite. So for example, if you just have minus x1 plus 2x2 less than equal to 10, you can essentially write it as minus x1 plus 2x2 between 10 and minus infinity. So to specify this linear program, I need C, D, A, H, L and U are inputs. Okay, so if somebody gives us these inputs, then we can try solving this linear program. Okay, notice that all constraints here are in the inequality form. So in case I have some equality constraints, so suppose I have x1 plus x2 equal to 1, I can change it into inequality form by saying x1 plus x2 less than equal to 1 and more than 1. So then it becomes equivalent to x1 plus x2 equal to 1, and it is in the form I want. Okay, so this form is called the general form of linear program. This is the most general form. Any linear program that is given to you can be very easily converted into this form by using transformations that I just mentioned. Okay, this is a bit difficult to work with when we talk about algorithms. So when we talk about algorithms, we talk about something called a standard form. So standard form of a linear program it is usually written as minimize C transpose X subject to AX equal to B and X greater than equal to 0. So this is same as minimizing C1 X1 plus C2 X2 plus Cn Xn subject to A11 X1 plus A1n Xn equal to B1 and m such constraints and these are all equality constraints. And x1 greater than equal to 0, x2 greater than equal to 0, so on and so forth. And these are your non-negativity constraints because they are enforcing that all x's are positive or bound constraints. If I have a problem which is not in this form, I can transform it into this form using some very simple tricks, which we shall try to see in the next class, and also see some geometrical insights about this type of problems. Linear programs are a very important subclass of general optimization, and they are very popular in practice. Many models in many different applications can be written as linear programs. Linear programs also appear as subroutines for solving more difficult problems. So this is sort of one of the most important classes of problems to work on, and we will be spending quite a bit of time on developing insights on how to solve these linear programs. So with that, we will stop this lecture and hope to see you soon next time.